everybody. Today, we're going to kind of continue on into section 3.4. Now, 3.4 has one idea, but it's updated. So, we're going to continue our discussion talking about how to do derivatives. So these derivative shortcuts. So far we've had this power rule. We've had how to do the derivative of e to the x. And we've had the product and quotient rules, right? And then we've had all those trig rules in the previous lesson. That wasn't on the test, but we did do that in between. Somewhere in there. It was a long time ago now, it feels like. Today, what we're going to learn how to do is how to do the derivative of a composition. So you remember, like, a composition is like f of g of x, where you have one function nested inside of another. So for example, yes, that is what this is going to be. Great way to read ahead. So for example, if I have the function what's the f and g? That's a composition. What is the inner function? What is the outer function? We're like, excellent. You guys see that? Okay, let's do another. This skill right now of being able to identify the inner and outer function and to see the composition as two discrete functions is critical moving forward. I would guess that probably 50% of derivatives from this point forward will involve a chain rule. So the ability to see the inner and outer is going to be like core. It's a core skill that we're going to have to be good at in order to be able to continue to be able to do these derivatives at a good rate. Now, we haven't talked at all about how to do the derivative yet for the composition. We'll get to that. But I feel like we need to make sure that we're competent on this skill before moving forward. Because if you can't do this, then everything after is going to be a mess, right? Okay, so this one is sine of e to the x. What's my inner function?
E to the x.
E to the x. And the outer? Sine x. I'm going to start making it trickier here as we go. What was that, Anthony? Good. So the outer, or the inner, is sine x. And the outer is 2x squared minus 3x plus 5. Or you could think about it. You could think about another way. Does anybody see another way to think about this? That's really the only piece that involves the composition, right? We know how to do the derivative of 5. We know how to do the derivative of negative 3 sine x. 2 sine squared x is the only thing we don't know how to do. Right? That's the only piece that's a composition. So if I think about that, what's the inner function there? Sine x, and the outer function is, Adrian?
2x squared.
Perfect, yes. Is everybody okay seeing it as two different things? Well, we know how to do the derivative of 5, and we know how to do the derivative of negative 3 sine x. So I don't care about that stuff. The only part that I don't have a rule for already existing is that 2 sine squared x. So that's really the only part that I have to worry about there being a composition. So you can think about it either way. I think the second way that we just talked about is probably the faster and easier method, because I can handle 2/3 of the problem with the existing derivative rules I have now, and only have to worry about that leading term. It's probably the easier way to deal with it. Now I'm going to start giving some examples where like that composition is snuck inside of some larger problem. So again, that trick here is going to be first identifying where the composition is occurring. Like here, we thought about it just occurring on that term. And then what the inner and outer is. Everybody's okay with that plan? So where's the composition? First. Good. That's our composition, right? That's one function smashed inside of another. The inner is 2x squared plus x, right? And the outer is e to the x. Nothing. So this would be a problem if I take the derivative. It's going to be a product rule with a chain rule stuck inside of it. That's going to be the rule we use to take the derivative of a composition. We'll talk about how to do that in just a second. Is that okay? So I'm just trying to mix in now like you're going to have these compositions inside of something else. Some larger problem where it's like, where's the composition at? Let me identify it. And then, okay, I've seen it. Now I'm going to proceed with the larger problem. Just like when we look at a quotient rule problem, before you start doing derivatives, you want to look at, is there a product rule inside of that quotient? Or if you have a product rule, is there a quotient rule inside of that somewhere? We'll do one more example, and then we'll get into chain ruling. Okay. Where's the composition? What's that, Adrian? On the inside of...
Inside of the cosine.
Okay. So you have that quotient inside of the cotangent that's the inner, is what you're saying, right?
Yeah.
Okay. And you said the cotangent then is the outer. That's good. Does anyone notice anything else though? Pat?
E to the x squared.
E to the x squared is another composition, right? I have a composition inside of a composition. Oh no, are you telling me this can happen too? Oh yeah. Oh yeah. So I have like a third like another composition inside of a composition, like a second layer. Okay. We're going to pause here and go into how to do the derivative of these compositions, and then we'll work through some examples of where we have layered these derivative rules now in one on top of another for a little bit. Okay? That's my goal today, is just to practice using these rules and using these rules in combination. Okay? So I'm going to actually I'm going to avoid my pre-done notes. I'm just going to kind of go from here because I feel like this is more organic. Maybe it'll be a little bit more effective. I feel like I haven't been getting you guys haven't been getting as much out of me as I would have liked to this point. So we're going to try to be a little bit more organic and conversational, go with the flow, and I'm going to just kind of try to put my thought process on the note rather than taking the note from the book. Try to map that a little bit, see if that goes any better. So this is the chain rule. So the chain rule is the derivative of the composition is the derivative of the outside function times the derivative of the inside function. Yes, go ahead, David.
Where's the non derivative of I know this is
Let's do some examples. Let's do some specific numeric examples of things. And if you're still confused as to what's going on, what the formula is doing, we'll follow up. Because it seems like you're having a hard time articulating it. I think the examples will clarify whatever is that we're hung up on. But let's do that, okay? We'll start simple with things that involve just the chain rule. And then we'll kind of layer, as we get going, we'll layer more stuff on as we get a little bit more comfortable. So the first thing you'd want to do is identify, is there a composition here? Yes, right? Can everybody see the composition? The inner function is 2x, and the outer function is sine x. Okay. So the derivative should be the derivative of the outer function. What's the derivative of the outer function? Derivative of sine is cosine. And then the inner function stays the same on the inside. And then we have times the derivative of the outer function. Derivative of the inner function. Inner. Derivative of 2x is 2. We're done. Is everybody okay with what we did there? Let's do some more, yes? That's mostly what I want to do today. It's just practice, like just doing the algebraic skill. We're going to pare this down a little bit. Derivative of the outer times the derivative of the inner. Not really. Okay, does everybody see a composition here? Okay, the inner is 2x plus 5, the outer is x to the 8. Great. Okay, so the derivative of the outer is, okay, 8 to the 7th, but the inside of that is an x, it's g of x, right? That's good. And then the times the derivative of the inner, which is just 2. And look at how nice that is, right? How would we had to do, take the derivative of 2x plus 5 to the 8th before? Yeah, you'd have to do the binomial expansion on that, which is a problem in and of itself. Like, that's non-trivial to do. That's going to take a minute. And then you have to differentiate term by term, and then hope you can factor it back again. But look at that, we did the derivative of that nasty, nasty problem in 30 seconds, and have it in a factored form that's easier to deal with if it's part of a larger problem. Ooh, boy, I like this. So this next one, our function is y equals 3x squared plus sine x. Do we see a composition here? Okay. What is the inner? 3x squared plus sine x. And the outer is e to the x. So the derivative of the outer is e to the stuff, right? And the derivative of the inner is? Correct. Make sure that you're putting a parenthesis there because it's times the whole thing. If you have a sum involved or a difference involved, you gotta be careful about that, but that's good. How do you guys feel on this so far? It's okay? I'm going to turn up the difficulty level a notch. So I'm going to now look at a situation where we have 2 chain rules going on, okay, in the same problem. So we're going to have one layered inside of the next. I should say y equals. Sine of cosine of x. Does everybody see the composition? You guys see 2 compositions, I hope, right? What's the innermost function? The x squared. And then the middle. And then the outermost. Okay, I'm going to stop writing these. Is that okay? Okay. So the derivative is the derivative of the outside. So cosine of this whole inside piece, right? and then times, I'm going to start writing, now that we're getting more than one layer, I'm going to start writing that as a discrete step, because it's going to be too much to hold in my head in one go. Is everybody okay?
Can you get down what the inputs are for this one?
So I gotta write it. Let's do. So let's see this. And then from here, the inside is x squared, and the outside is cosine x. That's probably the smartest way for me to write it, right? It's the clearest as to what's going on. Yeah? Okay. So when I do this derivative, that's going to require a second chain rule now, right? So I did one chain rule to get to here, but when I do the derivative inside piece, that's going to be another chain rule. Did you guys see that? Where they're like linking these things together. So I'm just going to copy that first factor down. Now if I look at cosine of x squared, the derivative of the outside is negative sine x squared times the derivative of the inside, which is just going to be 2x. So if I collect this all together, I have negative 2x sine x squared cosine of x squared. Let's do another one like that, right? That's rather challenging. You guys feel the layer, you see the layering that's happening on there? Again, I would encourage you, like I've done here, when you see that there's going to be multiple chain rules involved, do them as discrete steps. Don't try to do all the chains all at once. It's much harder to hold that all in your head at one time, especially when it's your first time dealing with this, right? So we're on E. So here we have square root of tangent of E. Actually, let me change that. I don't want to use tangent here. I want to use cosecant. You'll see why in a second, why I chose to do that. Not that it makes the problem harder, but it makes, or easier in any way, but something happens with that particular derivative that I want to highlight. Okay. So my first layer in my, everybody see there's a two-layer composition here, I hope? Right? The outermost is square root x. The middle is cosecant. The innermost is the x squared. So if I look at my first layer, my inner is cosecant of e to the x, and the outer is square root x. And then cosecant x, the inner is e to the x, and the outer is cosecant x. Is everybody okay with that? All right. So first thing I would do is I'm not going to think about that as a square root. I'm going to think about it as a fractional exponent. So I'm going to do just a little bit of algebra here to put it in a form where it's easier to do the derivative. You guys feel good so far? All right, let's do our first layer. The derivative of the outside is dealing with that, right? Yep, 1/2 stuff to the negative 1/2 times the derivative of our stuff so far so good? Okay. So now we have to deal with that piece. The rest, the first part, just we recopy. And that's not going to get touched. What's the derivative of cosecant? Okay, so it's negative cosecant of stuff times cotangent stuff times the derivative of that stuff.
Is that a big?
That was one of the trig derivative identities, yes. The derivative of cosecant is negative cosecant times cotangent. I remember, the easy way to remember that is that cotangent, or cosecant and cotangent both have sine as their denominator. Those are the two that go together. And that's all we are left to do then is take that final derivative, right? The derivative of e to the x is e to the x. And again, maybe there's a little bit of cleanup we could do here, but like quite frankly, I'm not terribly interested in it. Right, like what could we do here, cleanup wise? Maybe we should. Let's take a moment. There's some good cleanup that can happen here. Yeah, so we can multiply this guy and this guy together, right? We add the exponents. The exponent on this is 1, right? And nothing we can do with that cotangent worth doing. And whether you want to write that as a square root or not, that's either way is fine. But that's some good simplifying that could happen there. David?
What if the cotangent also with the negative squared? Is this the more?
No, because you don't, like the exponent is stuck on this guy, right? It's not around the whole thing. Does that make sense? And because it's all multiplied, I don't have to distribute it, right? Because there's no addition and subtraction. It's just two things multiplied together. So just, if I multiply whatever things together and I just have a string of things, right? A times B times C, you can just do A times C times B, which is what I did. Oops. And these all have primes on them still. Okay. Let's keep going, right? So we're going to notch the difficulty switch up one more. And now I'm going to start including product and quotient properties with chain rules inside of them, or chain rules with product or quotient properties inside of them. And the last layer of difficulty will be like unlimited mixing, where I can have like multiple chain rules inside of a product, or chain rule, product rule, chain rule inside of that product rule. You know, where we just like really layer these things on top of But the intermediate here is just one chain and then a product or quotient. Okay? Everybody good? So far? We feel okay with what we've been doing? Okay. You'll stop me and tell me if like I am hopelessly lost when I do something, right? Like, let it be known that if you are confused, there's more than one person in the room that's also going to be confused. That is going to be glad if you say something to stop me and ask some follow-up to slow down or to do something else. Okay, so don't be shy and feel like I'm slowing the whole class down because I had a question. I promise you someone else has the exact same question. They're just too shy to ask. So if you're stuck, or you're not sure what happened, or you don't see it, or you're in a bad place with it, like stop me and say something, okay? Yes, hey.
You always start with like the outermost thing, right? And you're just working on it.
Yes, it's like the order of operations, where if you were trying to evaluate that composition, you go from the outside to the inside to the inside to the inside. Yes, absolutely. That would be my recommendation. I mean, if you're very careful, you can start like inside out, and I wouldn't do that. All right, let's think of a good one. Here we have cosine of x e to the x. You guys see the composition. What's the other rule involved here? Product rule. Where's the product rule happening? X e to the x. Everybody see it? So my inner is this. I'm going to write PR next to it to note to myself that it's a product rule there when it comes time to do that. And my outer is cosine x. So the derivative of the outside is, negative sign, I'm going to say stuff, and then times the derivative of the inside. Everybody's okay with that? Okay. So copy the first part. And now to do the derivative of x e to the x, I need a product rule. Which again, I'm going to do in one step. I'm going to write out the product rule, and then I'm going to differentiate the parts. So I'm not going to try to do all of it in my head. It's too much to carry. I'm going to get lost and muddled and screw something up. Is everybody good with the work that I'm showing? And it's going to be really important as these start getting more and more complicated that you're able to keep good track of doing one thing at a time, staying organized. Because if you get something that has like chain rule inside a quotient rule, inside a product rule, with another chain inside of that, it's really easy to get turned around if you're trying to do too much at one time. Like peel one layer of your onion, get that peeled, and then go to the next layer. Don't try to peel the whole onion in one shot. Just take one layer off at a time. Is everybody good with how I got to the finish line here? Okay. Let's do another. What do we see here? See a quotient rule, right? Yep, that's good. Anything else?
The composition.
Where's the composition at?
E to the x squared.
E to the x squared. Which is the first one I should get to? The quotient or the chain? The quotient, right? Because I don't have to worry about differentiating 1 minus e to the x squared until I've gotten into the quotient, right? Does everybody kind of see that? So the order of operations here becomes hard, at least at first, to kind of get a handle on, but it just always from the outer in, always from the whole to the part. The quotient rule is derivative of the top times the bottom minus the bottom times the derivative of the top over bottom squared. Very good. So it's not until I do this that I need my chain rule, right? That's the only part of this derivative that involves that chain rule. You guys all agree? Okay. So over here, this guy's the only thing involved with my chain. My inner is x squared, and my outer is e to the x. I'm just boating through that because that's a composition we looked at earlier, right, when we were doing examples. Okay. So I have 1 minus e to the x, and that's going to be 0 plus e to the x when I do that derivative. Everybody's good there? Minus 1 plus e to the x times 0. And then to differentiate e to the x squared, I'm going to have derivative of the outside, which is just e to the x, times derivative of the inside. And maybe that's a simple enough derivative that you would do it in one step instead of doing the extra step. But I'm going to write out the extra step because these are notes. If you're going back to look at something, I want it to be like super duper crystal clear, like where the 2x comes from. Oops, forgot to copy the squared on that.
So you could just leave it at that, you don't have to solve it.
If this is a free response question, you could stop here, yes. Okay. Now, I think some nice simplification is going to end up happening if we keep on going. So I'm going to keep on going, but if this was a free response question, you'd be done here. Absolutely. Is everybody okay? Again, I think it's helpful to just kind of see the simplification, but know where the stopping points are depending on the context of the question. So I distribute this through. What's e to the x squared times e to the x? Nope. E to the x squared plus x. Remember, we're adding exponents when we multiply bases, right? Oof, I know. And then I'm going to do that, cancel my negatives. You guys good there? So I'm going to have plus now 2x e to the x squared. And then I'll have plus 2x e to the x squared plus x. Oh, I guess maybe nothing nice does cancel there. I don't think so. I was wrong. Nothing nice does happen. We just spoiled it out for no reason. We still gave us an opportunity to check on e to the x squared times e to the x. Make sure that we're feeling good on our exponent properties. That's worth doing. All right. I'm gonna do one more example because it looks like we're just about out of time. Okay. This is gonna be crazy town. Everybody ready? And this is a night right here, by the way. Let's count. What do we see here? I see 1, 2, 3 chain rules. I see 1 product rule, and I see 2 quotient rules. Right? Like this is a problem. This is a day's worth of work in itself. You guys, looking at this, do you see the 3 chain rules? Everything under the square root, everything inside of the sine, everything inside of the cosine. You see the product rule. Sine times cosine, and the 2 quotient rules should be pretty obvious, right? Because there's the 2 fractions in there that are unreducible to avoid. You guys cool? All right. Let's start peeling back the layers here. I know. So the first layer is the outer chain rule. Everybody's good with the first chain rule that we did.
Do we not do quotient and all that stuff with quotient rule?
Well, the outermost thing is the square root over everything, right?
Yeah.
So the first thing we have to do is this chain rule,
Okay.
right? It's going to be specific to the function, right?
Yeah.
So I'm looking at what's the outermost operation going on. The outermost operation is the square root of everything inside. That's a chain rule. Now, if I look at this derivative, what's the outermost operation going on now? The product rule, right? It's the multiplication between these 2 things. Everybody see that? So I'm just going to do this because I don't want to copy it again. So it's going to be times derivative of this plus this derivative of this Is everybody okay? Multiplication out of there, make sure it's clear. So now we've taken care of the product rule. Now we look at these 2 derivatives. What do I have to deal with first on those? They both involve a chain and a quotient. Which one's going to come first? Well, what's the outermost function in cosine? Is it the division or is it the composition? The composition's on the outside, right? It's cosine of the quotient. So we got to do the chain rule first in each of those 2. The last thing we're going to be doing is the quotient, because that's like the insidest of the insides. You see? And now I want to tell you, like, this is way beyond the scope of anything I would expect you to do on a quiz or a test. But like, if we can handle something like this and like see our way through it, like you are locked and loaded for going forward, because this is, boy howdy, is intense. And one more. Oh. That was supposed to be there. Don't need that there. Okay. And now my last layer is going to be these quotient properties, right? You guys cool? Again, this example is stupendously complex, way harder than something that you would encounter on a quiz or test, but I think is like really instructive, and it's bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared plus and then this guy, and then we have bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. That's awful messy. And then there's one more level to go where I differentiate the pieces inside the quotient. I'll let you guys finish that up on your own, because I know you're like dying to try this one again. So we'll do, next time we'll do some little bit more talk about chain rule, and we'll do some, I'll have a handout for you guys to work on in class. It's gonna be like summative of all the derivative rules at this point. And you might see a homework quiz covering like 3.1 through 3.3. So just the derivative rules, like taking derivatives of, like an equation involving, product quotient and trig.
That's what I put it away.
Don't chain on it. So the next one. Everybody okay? I haven't even assigned the homework.
Oh, okay. There's the other thing too.
The only thing to it is at 3.
Yeah. Oh, then what was the thing we had? It's like 3, like chapter, whatever.
Yeah.
It's just,
Well, I think it's section 3, because that wasn't part of your sentence.
yeah.
So I think that's the last. I think that's the only homework.
Have a good day.
You too.